Okay, so we're going to start with the first problem for your homework tonight is this one that's a little tricky to understand. Now, check this out. Here's a slide that explains the scenario. A child at the county fair wins 5 tickets. I think they do this down at the, or at least they used to do it down at the, what's the Labor Day thing that they have down in Malibu? The chili cook-off. You know, have you guys been to the Malibu chili cook-off? Yeah, you know, don't they have tickets? Yeah, so it's like tickets, and then you pay in tickets when you're inside the fair, the thing, right? So a child at the county fair wins 5 tickets. The redemption store carries the following items priced in tickets. So the items are A, B, C, D, and E. Apples, balls, cookies, dolls, earmuffs, whatever. And apples cost 3 tickets each, balls cost 3 tickets each, cookies cost 2 tickets each, dolls cost 1 ticket, and an earmuff costs 1 ticket. Now, does everybody understand the scenario, the situation? So here's this child with 5 tickets. And the question is, in how many ways can the child spend her tickets? That's the question that we want to solve. That's the problem we want to solve. How many ways? Well, look, just looking at it a little bit at random, can you give me a few simple examples of what the child can buy with 5 tickets? What could the child buy with 5? Just give me 1 or 2, just sort of at random. You could buy 1 apple, but then what?
Cookies.
How many cookies?
1.
Well, you could have 1 apple and 1 cookie. But you couldn't have any more because that takes 5 tickets. What else could you have? What's another possibility?
2 cookies and a doll.
2 cookies and a doll, etc., etc. Does everybody see how that works? Well, I suppose, well, no, not necessarily. I suppose, well, I guess it's always possible to spend them all because we have items that cost 1 ticket.
Yeah, but like, would she have to?
Let's, oh, I see. No. Oh, that's a good point. No, let's not include that in the count. And since we do have items that cost 1 ticket, it's always possible to spend all the tickets. So let's say that that's not included in the count. That's a good question.
You can't come back later for like a better price.
Yeah. Hoping that, you know, the prices will have, hoping that the prices will have changed or whatever. But anyway, okay, so let's just say that it's using all the tickets, all right? Now, can anybody tell me right off the top of your head how many different things can this child buy? In how many ways can the child spend her tickets? Does anybody know offhand what the answer is in this particular example? Does anybody have any idea how you would figure that out? Something with combinations and permutations, but I tell you, this particular example is, there's not a simple formula. Instead, what we're going to do is we're going to write a function that calculates how many ways. Are you with me? Now look. So here what we have is we have what does this look like? A Lisp, a scheme of what? This 33211. What does that look like? That's a list. And do you see that the 33211 represents the price of the apple, ball, cookie, doll, and earmuff, right? That's a price list. Are you with me? Well, before we go any further, is there a systematic way for us to list all the things, all the ways to spend the money? So let's do this systematically. What if the first item is an A? Then what other possibilities do we have? I think you gave one. An A and a C. What else is possible? A, D, D, A, D, E, and A, E, E. Is everybody with me that those are the possibilities for the ones that start with A, including an apple? But what if we don't include an apple? What about all the ones that start with a B? Can anyone give me the B's? The ones that start with a B? So what would it be? BC, BDD, BDE, BEE. Is everybody with me on that? You kind of see how this pattern is playing out. Now, what about the ones that do not include an apple or a ball, but ones that include a what? A cookie. So what would, but what would that be? Now you know that it's not going to include, we don't, if we do the one that has include a cookie, we don't want to have the one include a cookie and a what? An apple, because we've already taken care of the apple one. Yeah.
That top one for the B should be BC, right?
Oh, you're right. I have a typo in my slide. Thank you. That should be BC. But there won't be a typo in it whenever I do this, because I'm going to fix it right after class. So for those of you who are looking at this on the video, it's correct. Okay, and now what about the ones that start with a C?
CCD.
CC, yeah. Say that again. CCD,
CCE.
CCE, and then a bunch of what? C what?
With 3 Ds.
And then keep going.
C.
C,
2 Ds, 1 E.
well, yeah, 2 Ds and an E, etc. Yeah. So are you with me on this? So it's going to be CCD, CCE, and then CDDD, CDDE, CDEE, CEE. Yeah? Are we good? And then what? Come on, systematically. Then what? D. Well, actually what? D, 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 D.
4 Ds and 1
D, 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 D. How many?
4 Ds, 1
How many in the D column?
4.
4 or 5? Oh, we have a difference of opinion. How many in the D column?
Oh, how many?
How many in the D column? The ones that start with D.
6.
Oh, now we have 6. No, now we have 5. Oh, difference of opinion. What?
If there's an E column, then 5.
Well, there will be an E column.
5.
Okay, so 5. So D, 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 E, D, 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 E, E, D, D, E, 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 D, E, 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 and then what?
And then all E.
All E's. All right, count them up. How many do we have? Count them up. How many do we have? 20. So therefore, what should this, so therefore, do you see that our function named count combos? Now look, what does count combos take? The first element of count combos is a what? Is a list of items remaining to be picked from, and then what's the next the second parameter? What's the second parameter? Number of tickets. Number of tickets. And do you see then that by this count, if we do count combos 3, 3, 2, 1, 1, and then 5 tickets, that should be 20, because we just counted them up. That should be 20. How in the world are we going to do that? Yeah, we're going to use a tree. Now look. So check this out. Here's count combos with 3, 3, 2, 1, 1, and 5. And now, what are the two possibilities? How did we start enumerating those systematically? We said the first possibility is that she takes a what?
First tab.
Yeah, the apple. And then the other possibilities were not picking the apple. Are you with me? So here's what we're going to do. We're going to analyze this by looking at the call tree of count combos. And what's going to happen is, if we pick the first item, that is going to be a branch to the left. And if we pick, okay. And so if we pick the first item, how much money have we spent? If we pick the first item, then how many, what's the first item in this case, starting from the beginning?
3.
The 3 is how much the apple costs. So if we buy the apple, then what's left? How many tickets do we have left? 2. So do you see then that the recursive call will be to 33211 with 2 tickets left. Are you with me? But if we don't pick the apple for the first one, what will happen? If we don't pick the first item, then now we're not considering picking the first item. So what do we have? So what's the recursive call in this particular case? 3211, but with how many tickets?
5.
Still with 5. So do you see then that it's the cooter? Are you with me? So, going to the left, that's when we had the first column with all the apples, and then going to the right, that was everything else. Are you with me? So look how this works. Here's how the calls are going to work. Now watch this. This is not obvious. Now check this out. So we're starting with 33211 and 5 tickets. So the first call will be what? Tell me what happens when we go to the left.
Picks the first item.
So what will the recursive call be?
The same list with 5 minus 3.
Which is 2. So it'll be 33211 with 2 tickets. Now what will this one call?
3, 2,
Because there's going to be a left and a right.
3, 2, 1,
1.
with 5 tickets.
No. We're starting with 2 tickets, and each time we go to the left, what do? How do we go from the 5? How do we go from 33211 and 5 to 33211 and 2? What did we do? Yeah, and so what was the recursive call after that? What was the recursive call? It was the same what?
Same list.
Same list, but with what? What happened to the 5? Yeah, we subtracted the first one from it. So if we go to the left here, what will happen? Come on.
It will go negative.
Yeah, but that's all right. What will it be?
332 or 332.
Yeah, it'll be 33211 with what?
Negative 1.
-1. Does everybody see that? But now, because it's a -1, what will this return? It shows you there. Because this is -1, what will it return? 0. So there are no combinations. There is no possibility with that setup. So do you see that that's going to be like, are you with me? That's going to be a base case, right? So it's going to, there's no combination. Okay, but now what can we do? If we go to the right, how do we go to the right?
3, 2, 1, 1, 2.
It'll be 3, 2, 1, 1, and 2, right. But now that we're here, what will this do? Remember, each one goes to the what? To the left and to the right with these rules, right? So now if 3, 2, 1, 1, what will happen? What will happen here?
3, 2, 1, 1,
The left is negative.
Oh, yeah, 3, 2, 1, 1, -1. Yeah, okay, 3, 2, 1, 1, and so what will that return? 0, because that's not a possibility. But now if we go to the right, what will happen? 2, 1, 1 with a 2. And now if that goes to the left, what? 2, 1, 1, 0. But now that means, aha, no tickets left over. So now how many combinations did we do? 1. So that returns the 1. Are you with me? And what did the child buy there, by the way? Which scenario did that represent?
Apple and cookie.
Apple and cookie. All right. And now, how will we go to the right? So now what happens if we go to the right? Instead of going to the left and picking the apple and the cookie, if we go to the right, what happens?
1, 1, 2.
Yes, 1, 1 with 2 tickets. A list 1, 1 with 2 tickets. And now how does this one pan out? When this one goes to the left, what?
1, 0.
I think it's 1, 1, 1, isn't it? Because the first item costs 1 ticket. Are you with me? So that's a 1, 1, 1. But now what happens with the 1, 1, 1? The list 1, 1, and 1. To the left is what? Is 1, 1, 0. Now does that work? Right. Okay, so that returns 1. And now how do you go to the right from 1, 1, 1? List what? List 1 with how many tickets? with 1 ticket. And now how does this one work? Yep, 1, 0 here, and that returns 1. And now how do we go to the right?
Empty list.
Empty list with 1. But now if it's the empty list, what happens? Yeah, 0. Okay, so now how many do we return to the, so what do we return up to the, when we return from the list 1 with 1 ticket, how many things did we have under there? 1 plus 0, which is what? 1. So do you see then that returns the 1 up to there? And then what does the list 1, 1 with 1 return? 1 plus 1, which is what? 2. So that returns the 2 up to here. And now what does this list 1, 1 with 2? Now what does it do?
Go to the right.
It goes to the right. And what happens when it goes to the right?
1, 2.
Yeah, list 1 with 2, etc. And there's some more etc. stuff. And there will be 1 possibility there. And then what will that return? The 2 and the 1. The 3 will return back up to here. And then what will happen here? The 3 and the 1 will return the 4. And then what will happen here? The 4 and the 0 will return the what? The 4. And then what will happen up here? The 4 and the 0 will do what? Return the 4. And then what will happen up here? The 3, 3, 2, 1, 1, 5 will go to the right. And what will that be? What will that be? 3, 2, 1, 1 with 5 tickets. Are you with me? And when it does all of its stuff, what will that return? 16. And then what will happen, get returned? The 20. And does everybody see that 4 are the 4 in the left one that includes the apple? Are you with me? Excellent. So, count combos, 3, 3, 2, 1, 1, 5. Let's define count combos. It's lambda prize list amount. Okay, are you with me here? The base cases are all your problem. The book has actually given us what to return. Now, can you tell me all those cases are, that's what you have to do, the ... But now, the book has actually given us what gets returned. So what gets returned if we're not in the base case? Can you? It's the one to the left and the one to the right. So we have to add the one to the left and the one to the right. So what's the one to the left? Count combos. Yeah, count combos of what? Say it again. Count combos of prize list and what for the amount?
Minus amount, car, prize list.
Yes. Is everybody with me on that? Is everybody with Adam on that? Count combos, the prize list, and minus the amount of the car of the prize list. Are we good with this? Because what did it do when it went to the left? It subtracted that first amount, right? So the same prize list. Are you with me? And so it adds that plus what? This next one is easier. How do we go to the right? How do we go to the right? Count combos. Now, did we use the same prize list? So what did we use? The cutter of the prize list and the same amount. Ta-da! Are we good? And it's all you have to do is do the ... But it's a little trickier than you might expect. But I think you can see from this tree how it works. Are we good? Is everybody clear? All right. So anyway, that's one problem for tonight. And then the next problem for tonight is about trees. So let's see how the trees work in Scheme. Okay? Now, here's the thing about trees. What is the native, what's the native data structure in Scheme? What's the built-in data structure? The what? What's the data structure that is the primitive data structure in? It's the list. So in order to process trees, we are going to have to use a list representation of a tree because trees aren't built in. Are you with me on this? Okay, now before we do this, I want to show you, go through a little demo. So let's go into demo mode. All right. So let me turn on my Okay, so here we are in our demo. Now watch this, sports fans. I think you will like this. First, let's review a little bit. Let's do a car of quote, quote, A, B, C, D, E, F. Can anybody predict for me what the car of this is? It's the list AB. Good. Okay, and actually I'm going to be doing a lot with this. Let me just copy this. Okay, and the next thing is the cooter of this. Can anybody tell me what the cooter of this is? Yeah, the list of the list CD and the list EF. Is everybody clear on that? Now, you guys, check this out. What do you suppose the car? Well, what do you suppose the car stands for? It's not just the car, it's the car. It's the what do you suppose what is it? It's the
So you take the first element of that list and then take the first element of the list.
Yes, what you said is correct. It's the car of the car. Are you with me? It's a shortcut for being able for writing the car of the car. So what's the car? What did we say the car was? List AB. So what's the car of that? Now, does everybody see that that's how that works there? Right? All right. Well, if we have a car, we also have a catter. Now, what's this? It's the, what's this? What is the, what by definition, what is the catter? It's the what of the what? It's the car of the cooter. Well, what did we say the cooter was? That list of list CD. So what's the car of that? CD. List CD, right? Is everybody with me on this? And what is the, I don't know how to pronounce this, kadar. What's the kadar of that? Or what's the, yeah, this is the what of the what? This is the cooter of the car. So what is this? Just B? It's list B, which is different. Are you with me on that? Is everybody with me on that? That's the, and if there is a ka'ar and a catter and a kadar, there must be also a what? Come on. A kadudder, which is the what of the what? Which is the cooter of the cooter. Yeah? And so what's the cooter of the cooter? Let me see. The cooter was that. What's the cooter of the cooter? What's the kadudder? List EF?
Double list.
It's the list of the list EF. Yeah? You are right. Is everybody with me on this? And guess what? And guess what?
Can you have as many A's and B's as
What is the CADDR? Let's do 2 more. So what's this one? That's the what? Isn't that the car of what we had before? Isn't that? Are you with me here? Is that the car of what we had before? That's the car of the cooter of the cooter. So what's the car of that? Can anybody tell me? Say it again. That's the list EF is right. And what is the cooter of the cooter of the cooter? Oh, good call. That's the empty list, right? Because the cooter of the cooter only has one item in it, which is a list. So that's the empty list. Now, is everybody clear on how all of this stuff is working? Are we good? Okay, now let's go back to our slides. Now, so we first start off with the definition of a tree. So what's the definition of a tree? Well, do you remember the definition of a list? It's kind of similar to the definition of a list. Do you remember the definition of a list? Well, let's review it. What was the definition of a list?
It's either the empty list.
It's either the empty list or it has
the car, which is the first element, and the cooter,
which is the rest of the list. So what do you think about the tree? So it's either the what?
empty tree.
It's either the empty tree or it's a what? Or it's a what? A non-empty tree with 3 parts. Okay, and what are the 3 parts? The root, which is an element, the left subtree, which is a tree, and right subtree, which is a tree. And notice that root and left subtree and right subtree are in computer font. That means these are probably going to be what? Scheme functions. Are you with me? So here's an example. Now look. Here is my tree. And so if we define my tree this way, quote, now, do you see, what did we say? First of all, is it empty, yes or no?
No.
No. So how many parts does it have? So how many parts does it have? It has 3. Can you see the 3 parts in there with all the parens? It's kind of hard to see, actually. But do you see that the 4 is the root, and then all that stuff, the paren 2, paren I, empty, empty, paren 3, empty, empty, and then paren, that closes out that paren, and then the 6, and then the 5, paren, 7, paren, that closes out that one. Are you with me? So if we were to draw this, what would it look like? If we were to draw, 4 would be the root.
And 2 and 6, the root of the left and the trees.
Yeah, and then the left would be a tree with a root of what? 2, and the right would be a tree with a root of what? 6. So does everybody see, is everybody with me that this is the picture of the tree that in scheme we have to write like that? Is everybody good? Okay, so that's my tree. So let's go back to our demo. Now, check this out. Use guys. Oh, by the way, see up here we said define my tree, and this is exactly how it was defined on our slide. So look, do you see then if I say my tree, what do you suppose is going to happen? All that. Yeah? Because we defined it. Just so I don't have to retype everything. And here is a picture. Actually, our author has given us a little picture here with all the indentation of what this tree would look like if you used the indentation for the children. Right? Okay, so now let's do a little demo. Let's do of all these functions, and then we will write them. Let's do make empty tree. What do you suppose the empty tree is? So if I just type make empty tree, what should come out? What should come out? How do you suppose we represent the empty tree?
Empty list.
The empty list. Okay, good. Yeah, are we good? And how about if we say make non-empty tree? Make non-empty non-empty tree. And now make non-empty tree is going to take 3 items. It's going to take a root value, so let's say 4, and then a left tree and a right tree. So just to keep it simple, let's just do it like this. So what will make non-empty tree do? What should this return? What should this return? Yeah, list 4. Oops. Did I misspell that wrong? Oh, I misspelled it. Darn. It's non-empty shouldn't have a hyphen. So let me do it again. Make non-empty tree, and then 4. Okay, so there we go. Are we good? And now how about this one? Just to show you, how about make non-empty tree. Now watch this. And let's just say 99 and my tree. Now what should this give us?
Does that need 3 parameters?
Oh, it does. Oh, wait. Oh, right, it does need 3 parameters. Oh, thanks for pointing that out. It's going to be make 99 the empty tree, and then my empty, and then my tree. Yeah, ooh, thanks for pointing that out. We have avoided some ugly red errors. So what will this be? 99, and then a list, 99, and then the empty list, and then all that stuff for my tree. Is everybody good? Okay. Now how about root? What should this return? Root, my tree. What should that return? 4. And what should left subtree so what should left subtree my tree return? What should that return?
2. 4.
Just 2?
The list
The
of
tree
4,
of
2.
root 2.
Yeah, so it should return parentheses what? 2 parentheses, 1, left paren, right paren, left paren, right paren, right paren, and then 3, left paren, right. Are you with me? It should return the whole subtree, yeah? And then obviously what should right subtree my tree return? What should that return? 6, 5, blah, blah, blah. Yeah? Okay, let's start doing some writing. Let's write, so let's write make empty tree. Are you ready for this? Define make empty tree. So I erased it. But anyway, do you remember what make empty tree returned? Just the empty list, yeah. So how many parameters did it have? How many parameters did it have?
0.
None. So lambda, no parameters. And what does it return? Just the empty list. All right? And the next one's going to be non-empty tree. Ooh. Here's our examples of make non-empty tree. Now, so what does make non-empty tree?
So these functions aren't primitives.
No, they are not. They are not. Good point. The question was, are these functions primitives? And they're not. So we're defining them here so that we can process trees. Because the native data structure is the list. Okay, so how do we make a non-empty tree? How many parameters? 3. So it's lambda root, left subtree, and right subtree. So now, what does it do? This is a one-liner, actually.
List.
Yeah, it's the list with those 3 things. Yeah? Remember how list worked? If we say list, quote A, quote B, quote C, that puts them all together in a list, right? Is everybody good on this? Okay, and then the next one is check this out. I forgot to demo this. What about What about empty tree? Empty tree, is this tree empty?
Yes.
Okay, and what about empty tree, my tree? What about that? Is that empty?
No.
Okay, so what about empty tree? How many parameters? One. Oh, shoot.
Does it mean
Yeah, it's just the same as null, right? So that's just a renaming null. Okay? And what about root? We did root. Didn't we do root? It's not there anymore. But if we said root, yeah, what is root? The root is just the what?
the car goes?
Yeah, it's the car. So define root. So now what should I put here? Should we say how many parameters does root have?
Just car.
It's just car. Yeah, good deal. And how about left subtree? Oh, now how about left subtree? Remember what is here, up here, left subtree, my tree. So what's left subtree? Define left subtree for me. What is that? What is it? It's the what?
The car of the tree.
That's the car of the cooter. So do I have to, so what? Yeah, exactly. So it's the CADR. And what's the right subtree? Ooh, what's the right subtree? What's the right subtree? I don't think you were quite right, but you're close, but no cigar. What? What is it? Yeah, it's the CADD. It's the cooter. It's the car of the cooter, right? Yeah, think about that. It's the car of the cooter. Because it's the third, you got to pull off the third one. So it's the CADDR. Yeah? Is this good? Okay, now next thing we want to look at is what is a search tree? Okay, so here, let's go back to our slides. The definition of a binary search tree is, and this is abbreviated BST. Does anybody know what the definition of a binary search tree is? Well, first of all, it's a binary tree, right? But what properties does it have? In order for it to be a search tree, they have to be in a certain order. Do you remember that from your data structures or your... Actually, we haven't done it yet in data structures. But if those of you who've had, huh?
Doesn't everything have to be on the same level or something?
No, it doesn't have to be on the same level. Now, you know what you're thinking of. You're thinking of a heap. Or no, you're thinking of a B tree. Actually, you're thinking of a B tree where all the leaves are on the same level. Yeah, that's what you're thinking of. But what about the search tree? Remember how that worked?
It's like a linear search.
No, it's not a linear search. It's the opposite. It's a binary search. So what, in order...
The example you gave was one.
Actually, the example I gave was a binary search tree. But what has to be, what about the order?
All the ones to the left are lower than it, all the ones to the right are higher.
Then what?
The root.
The root. Okay, so here we go. Every element in the left subtree is less than the root. Every in the right subtree is greater than the root. And the left subtree is a binary search tree, and the right subtree is a binary search tree. Are you with me? So look, with that in mind, let's go back to our demo. Let's see, check this out. Let's start with a clean slate here. And let's do my tree. And let's see if how in works. In, question mark, works. So in 6, my tree. So what should this return?
True.
This should return true because 6 is in my tree. Whereas if I do in 99, my tree, what should that return? false, because it's not in there. Now, what's the most efficient way to define in? What is the most efficient way to define in if the tree is a binary search tree, so that it has this property that all the ones to the left are less than or equal to the... So define, and how many parameters does in have? Does it? Oh yeah, it does. 2, and what are they? The value and the tree, yeah? So now what's the first thing we do? What's our base case?
If it's the empty tree.
If it's the empty tree, what do we return?
False.
Correct. So we're going to use a condition here. By the way, did you guys notice when I handed back the homework that a lot of people aren't comfortable, want to use nested ifs a lot instead of condition anyway. So condition, our first one is empty tree, we return false. But now, if it's not the empty tree, what do we know that it has? If it's not the empty tree, what do we know that it has?
It has the 3 parts.
Yes, which is a what? A root and a left tree, subtree, and a right subtree. So now what do we check?
If the value that you're looking for is
For-
greater than or less than the root.
Then the root. Yeah, so equals, well, let's see if we find it first, right? So equals value root tree, then what? We return true. Otherwise, what's our next condition? Less than. So less than value root tree. But now if it's less than value root tree, what do we return? In, yes. We check to see if it's in what? In value left subtree of tree, right? So in value left subtree of tree, else what?
In value right subtree.
Yeah, else the value must be greater than the root in value right subtree tree. Look how easy that is. Is that just easier than falling off a log? Okay? Now, you guys haven't heard that expression before? Okay, now, what's one thing we always do with trees and data structures? We do what? Traversals, right? What are the traversals? In order what? Pre-order, post-order, in order. Okay, so let's look at pre-order traversal. So a pre-order traversal, now what our scheme version of traversal is going to do with a tree is it's going to return a list, right? So check it out. And what's the definition of a pre-order traversal? If the tree is not empty, well, if the tree is empty, what list do we return? Just the empty list, right? But if the tree is not empty, what do? We visit the root, then we do a pre-order traversal of the left subtree, then we do a pre-order traversal of the right subtree, right? So can somebody tell me what is, if this is my tree, can somebody tell me what is the pre-order traversal of this? What's the list that should get returned? 4. Come on. 2, 1, 3, 6, 5, 7. Now, this is review, right? Is everybody good with this? 4, 2, 1, 3, 6, 5, 7. Okay? So that's what should get returned. We want to return that list. Yeah? So it's actually, here, let's go back and do to our thing. If we say pre-order, now watch this. If we say pre-order my tree, that's what should happen. Yeah? 4, 2, 1, 3, 6, 5, 7. Okay, so can we define pre-order with append? Oh, do you remember how append works? Remember how append works? If we append, quote, ABC to quote, DEF, Remember what that does? That's different from list A, B, C, D, E, F, right? What is append? It does this. It appends to lists. Are you with me? That's different from list A, B, C, D, E, F. Is everybody with me on this? Because that's that. Yeah. But if you use append, pre-order is pretty easy. What do you? Well, first of all, what's the base case? Lambda tree, and what's the base case?
Empty.
It's the empty list, right? So if what?
Empty tree.
If empty tree, return
Empty.
empty list. Otherwise, what do we return? Now, can you see what to return next? Otherwise, we do the what of the what. Come on. You should know, you should be able just to say this one.
You append 3 things.
You don't want to append 3 things because the first thing, I think what you want to do is the 2 things you want to append. What 2 things do you want to append? Look, what do you want to append? What 2 things do you want to append? You want to take the what?
Left sub.
The left subtree, the what of the left subtree? The pre-order traversal of the left subtree, and do what with that? Append that to the what? Pre-order
Of the right.
traversal of the right tree, and then what do you want to do with that? See, because this 213 is a pre-order of the left, the 657 is a pre-order of the right. And then what do you want to do to that? Cons the what? The root. Yeah? So look. So what will this be? The very first one will be what? Cons the what? The root of the what? Of the cons the root of the tree, right? Are you with me? So you want to cons the root of the tree with the what? With the append, yes, keep going. So cons the root of the tree with the append of the preorder of the left subtree of the tree with the with the preorder of the tree, yeah. So append the preorder of the left subtree of the tree with the preorder of the right subtree of the tree. Yeah? Now, do you see that this is really inefficient? This is really inefficient. Why is this inefficient? Because each time it calls itself, it's doing append. And can you imagine what append does? Append is, yeah, you have to go all the way down the list to do the append. Okay, so I'm sorry this one's going to be really quick, but we need to do it. So look, we're going to make an efficient version. This is going to be called preorder onto. Now watch this. The way this is going to work is preorder onto, we're going to have, now this is going to be our helper function with one extra parameter like we're always used to, right? And what preorder onto is going to do is it's going to take the preorder, it's going to take the preorder of this and put it onto the quote ABC. Actually, let me go back to let me do that. Let me show you one. So check this out. Preorder onto of my list and the list ABC. Or, I'm sorry, it's my tree, right? Now watch this. So what Now, do you see that this is what preorder onto my tree list ABC does? Because what's the preorder? Because what is the preorder of my tree? It's 4, 2, 1, 3, 6, 5, 7. So that puts it onto the list ABC. So look. So what does the preorder onto of this do? Check it out. Well, what does it have to do? It has to take the what? The right subtree and do the preorder onto of that with what? With ABC. Are you with me? Now watch. So it's going to take the preorder onto of the 657 and put that onto this. And now what is that going to produce? 657 ABC. Is everybody with me on that? And then, now that you have the 657 and the ABC, what do you do? The preorder onto of the what? Yeah. Now we're going to take the preorder onto of the left subtree, but we're going to preorder that onto what? Onto the 657 ABC. Are you with me? And once we do that, what will we have? The 213 657 ABC. And that's going to be 213 657 ABC. But now that we have that, the only thing we need to do is what? Cons that into this. Boom. And we'll have this without append. With no append. And isn't this exactly the same kind of thing that we did with reverse? You know? It's this, so look, so can you tell me what is, here, can you tell me what is the defined preorder without append? So it's going to be the it's going to be the preorder onto, and we'll just preorder onto our tree with the what? With the empty list, yeah? So now, what is the preorder onto? Lambda tree and list returns a preorder of tree appended to list, but without using append. So if empty tree, tree. Oh, then we just return the list, right? If the tree is empty, we just return it. But otherwise, what do we return? Now, can you say it based on what we just looked at? It's the what?
The preorder onto.
Well, the very first thing that we had to do was, what was on the, we have to cons the what? The root of the tree. So cons the root of the tree, right? Good, good. Now what? With the what? With the preorder onto of the left subtree of the tree of the preorder onto of the right subtree of tree. Oh, and list. And that's it. Now, your problem for tonight is to do the in order onto. Okay? So that's why we needed to get through this. So sorry I kept you a little later, but I think this is all you need to know for doing the homework for tonight. Yeah? Are we good? Okay. So, we'll see you next time.